Next talk, the next talk in this session, it's a pleasure to introduce Antonio Viruel from the University of Malaga in Spain. And I believe that the full title of his talk is Permutation Representation of Finite Groups via Automorphisms of Idempotent Evolution Algebras. Professor Viruel.
Thank you very much. So first of all, let's thank you all for being here and for the kind invitation for allowing me to talk about this subject in this seminar. So I'm going to report about this joint work with Cristina Costoya from the University of Santiago de Compostela and Pedro Mayorga, who is a brilliant undergraduate student here at Malaga. And I will start just introducing the main subject, or the main object in this lecture that will be representation of finite groups and evolution in algebras. So let's check. Yeah. So by representation, I mean, of course, a representation of finite groups. And well, from the very beginning of group theory, we think of groups as group of symmetries or symmetries of mathematical objects, or the group of the full group of automorphisms of a mathematical object. So we are involved in a long-term project with Cristina Costoya, in which the main subject is just giving any category C. We would like to know whether any abstract group can be represented as the full group of automorphisms of object in C. And well, beside of being important for the people working in the category C, since you can do kind of a Galois theory for that object X by looking at the algebraic properties of H. Here we are also interested in purely group theoretical representation theory, since anytime we can realize a group H as the full automorphism group of object C, we got a collection in which is indeed an invariant of H, and then all the C invariants of the objects X will be invariants of the group H. Nevertheless, I'm not going to be much clear how. So then, yeah, something says
your sound disappeared for a short while. There was a freezing of it.
Oh,
it's now back.
It's okay now. Okay, yes. So thank you for letting me know. So then the okay, so in that way, representation group representation theory is going to show up here. So I'm interested in showing that some groups show up as the full group of automorphisms of an object in a category C. And then the category C we are considering today is that of evolution algebras. So evolution algebras were introduced by Tian in his PhD thesis, as far as I know, back in 2004, and they were kind of inspired by the work of Therington on genetic algebras. So, well, Therington thought that the algebra could model classical Mendelian genetics, in which two parents symmetrically contribute to the offsprings, to the genetic information in the offsprings. So if you have two alleles, A, capital A, and lower A, and they are kind of equally probable, then you get this kind of a gametic or genetic algebra in which for all genes, you can think of each row and column is just how the parents contribute, and then the multiplication table is symmetric because both parents contribute in the same way, and then you got this kind of a table that gives up commutative because both parents symmetrically contribute to the genetic offsprings. It's non-associative as well. In this easy example, you can just check that if you somehow breed two parents with a lower A genetics, and then you breed that with a double capital A, you get a kind of a mixture AA, while if you first breed in this right part these two parents, and then with this one you get a completely different thing. So then the idea of Tian was, okay, let's think of a sexual propagation in which it doesn't make sense that there are two parents, so it's just a gen is or allele is just reproduce itself. So the multiplication table is automatically symmetric because there is only one gen, and it only makes sense to consider squares of elements, right? Because you cannot mix up two different alleles. Right, and again, you get something which is commutative because I mean you can just multiply a thing by themselves, and well, generators by themselves, right? And it's again non-associative because again here, if you just breed to reproduce one gene A2 and then A1, you get a completely different thing if you do this thing, because first this multiplication vanish and there is no sense of keep on breeding. So let me give you the precise example, the precise definition of an evolution algebra. So an evolution algebra will be just algebra over a field K, in which the new thing is that it's not defined by the identities, but the existence of a basis, which can be thought like an orthogonal basis. So elements in this basis can have non-trivial multiplication only in case they multiply by themselves, right? And such base is called a natural basis. Well, since the multiplication is given by a natural basis and you have to worry only about the squares, so then the algebra structure of B is fully determined by just looking at the squares, right? And these squares will be expressed like a linear combination of the rest of the elements of the base. And then we should call this mu iota like the structure constants of the algebra X. And then you can associate a matrix that we are not going to use today that is called the structure matrix. Okay. So let's show a few examples how to construct evolution algebras, and you will get a clear picture of how these structures are. So first, let's start with any vector space in which you got a symmetric bilinear form. Then choosing a vector W in V, you can define a K-algebra structure in V by defining multiplying two elements is just to make the this scalar product, and then you multiply the result to the vector W. Call this XW K-algebra, and then if the characteristic of the field is different of two, then you know that you can diagonalize that symmetric bilinear form or the associative quadratic form, and then you can construct orthogonal basis for that Euclidean vector space, let's say, and then that becomes evolution algebra in which natural bases are in one-to-one correspondence with orthogonal basis of this vector space endowed with the symmetric bilinear form. So this example shows that although evolution algebras are defined in terms of natural bases are not unique. So you may have one evolution algebra and have be defined in terms of two different natural bases. And the second examples that illustrate the situation we have here, this is a kind of a dot example. So let's think of a three-dimensional vector space, and choose a base x1, x2, x3, and define the multiplication in there given by this multiplication table. Again, I only just telling you which are the squares. So x1 squares is x3, x2 squares is x1 plus x2, and x3 squares is x1. And then just define y to be the ideal generated by x1 plus x2 and x3. And if you look at the multiplication, when you multiply x1 by x1 plus x2, you get again x3, and then when you well, if you do the math somehow, then happens that y is an evolution algebra in which you can find a natural basis, which is x1 plus x2 and x3. And the funny thing in this case is just the natural basis of y cannot be extended to a natural basis of x, right? So you got an algebra morphisms, which is the inclusion of y in x, and happens that the natural base of y cannot be extended to a natural base of x. So in general, in evolution's algebras, algebra morphisms doesn't map natural bases into natural bases. So yeah, the point is that since evolution algebras are not defined in terms of identities, but defined in terms of existence of a natural basis, and we have seen that these natural bases are not preserved by algebra morphisms, they are not unique, then evolution algebras don't have a kind of a nice structural properties, right? And like a kind of joke, evolution algebras are not hereditary, right? And they are not hereditary in the worst in the worst situation, right? If you give me any finite dimensional commutative algebra, you can always find a finite dimensional evolution algebra containing A, right? So any commutative algebra can be seen as a subalgebra of an evolution algebra. So in order to get rid of that kind of a not that nice properties, we are going to restrict ourselves to a special class of evolution algebras. These are called idempotent evolution algebra. And an idempotent evolution algebra is nothing but an evolution algebra in which when you square it, you get all the algebra again, right? And they are nice because different natural bases are just well, I mean, there is just one natural basis up to rescaling or ordering the elements in the base, right? So essentially there is only one natural base, and that is pretty nice when you want to compute automorphisms, which is what we are doing in this work, right? So there is this theorem by Alberto Duque and Alicia Labra. Thing is back to 2019, but probably earlier. So given a finite dimensional evolution algebra, and then you fix a natural base, which is again unique up to rescaling or reordering because the evolution algebra is idempotent. Then whenever you get an automorphism there, then the main basis is going to be another element, another natural base. So it's going to be just rescaling and reordering. So that's allow them to define a natural permutation representation of this group into the symmetric group of rank n, the same the dimension of the evolution algebra, and the even compute. I mean, this is a representation. It's not a short exact sequence, but as exact sequence. So they identify the kernel of this map and happens to be an abelian finite group, which is somehow expressed in terms of a root of unit of K. So in particular, so we get finite groups all around. So the automorphism group of an idempotent evolution algebra is a finite group. So recalling, we got a finite dimensional evolution algebra, which happened to be idempotent, and then we know that we got a finite group in there, and there is a permutation representation in which we know the kernel is an abelian one. It's an abelian subgroup of the group of automorphisms. So then you got two different problems, two different questions to answer, depending which of these two properties you focus your attention. So first, since the automorphic group is a finite group, then you can ask which groups could be represented at the full group of automorphisms of a finite dimensional idempotent evolution algebra. And the second problem is whether, given any representation with abelian kernel, that representation can be induced by or realized by the group of automorphisms of an evolution algebra, right? And we are going to attack these two problems in this lecture, and also a third one, which is a variation of problem 2. So for the problem 1, we have a pretty good knowledge of what is going on. So for any finite group, you can always find a kind of evolution, an idempotent evolution K algebra X, such that G is the group of automorphisms of X, and you can do it whatever. I mean, I'm going to just present chronologically the results. So Cibron tries to prove that whenever the base or the ground field is of zero characteristic have no torsion, then you can do it. That in 2020, Costoya, Ligurus, and Tocino and myself, we found that you can do it for any given field. And last year, Costoya, Muñoz, Tocino, and myself, we found that if the ground field is big enough meaning that the units in that field is bigger than twice the set of the finite group, then X can be chosen to be a simple evolution algebra, right? And these restrictions in the characteristic here and the set of the field is just because you have to solve some equation, and you need enough elements in your ground field to solve that equation. But this proof is slightly, well, I mean, different. And since we are going to use the ideas in this proof, I'm going just to recall how this is proved, right? So the idea is going through graphs, and we are restricting ourselves to a subcategory of the category of graphs, which is the finite. We are considering only finite simple. So these are not quiver, just simple graph and directed graph. And then morphisms are going to be just monomorphisms, right? Once we fix that category, we construct a fivefold functor from this category of graph to the category of evolution algebras over any field, such that for any given graph, the algebra is going to be idempotent. And then this is the important thing. We are preserving the group of automorphisms. So it's just faithful and full on an automorphism. And how this is done? So essentially, when we are given a graph, we are given a set of vertices and edges and some adjacency relations. So we are constructing as a vector space, or evolution algebra is going to be spanned by both the vertices and the edges. And we are defining a multiplication table in which vertices are idempotent elements, and edges, the square of an edge, codifies the adjacency relations of that edge, right? So if the edge connects the vertex U and the vertex W, then E squared is itself plus U and W. So then every automorphism of the graph induce an automorphism of the evolution algebra, and any automorphism of the evolution algebra induce an automorphism of the graph, because idempotent have to be preserved and edges have to preserve adjacency. So, and then the final point in the arguments is just that given any finite group, you can always find a finite simple graph in which the group of automorphisms of the graph is the finite group you start with, right? So that's the way you prove that every finite group could be seen as the full group of automorphisms of a evolution algebra. So let me show you an example of how this thing goes. So we all know that we can just think of the base field as an evolution algebra by just thinking that there is a one-dimensional one. The generator is the unit, so b squared equals b, and then this will be a rigid evolution algebra in the sense that the group of automorphisms of this algebra is the trivial group. But you can just get way more examples of evolution algebra with trivial group of automorphisms just by considering a graph like this one. This graph have a trivial group of automorphisms, so there is this half degree 3, but then the length of these tails are different, and then you can just construct a K algebra by spanning considering the vector field spanned by the vertices and edges, and then making this multiplication table. Okay, so let's recall again our problems. We have an opponent evolution algebra, and the two problems were either find finite groups represent finite groups at the full group of automorphisms, and then the second problem is trying to realize or represent permutation representations by automorphisms of idempotent evolution algebras, right? And we have a pretty good answer for problem 1, and then we are going to look at the problem. So let me first recall and focus on these problems. So again, X is an idempotent evolution algebra with natural basis, and then we got an automorphism there, right? So, and these automorphisms have always this kind of a picture, and then the permutation representation is just by looking at this permutation in the subindex, the way we reorder the elements of this space, right? Then the algebra automorphism is completely determined by what is going on at the squares, right? And if you do, express these squares and then compare coefficients, essentially deciding whether we got a graph algebra automorphism is just checking this equality, right? So essentially, that means that whenever we got automorphisms, this permutation representation somehow reduced to understanding pairs or couples, or in general tuples of numbers of indexes, right? So let's introduce a little bit of group theory that we are going to use, and just to recall that if I gave you a permutation group, so I'm thinking just finite groups inside symmetric groups, it will be called K transitive if whenever we got K tuple of this distinct pairwise different numbers, two of these tuples, the group will be called K transitive whenever you can find an element sigma in P mapping this order tuple to this one, right? So x1 have to go to y1, x2 to y2, sk to yk. So again, let me illustrate with a few examples. So whenever you got a regular representation, so we think of a group acting on itself by left or right multiplication, it really doesn't matter. You got a one transitive or just simply transitive group. If you think, forget something more kind of geometrical and easy to understand. So if you think that the identical group of 8 elements, like, and you see that group as the group of symmetries of a square, but you look only how those symmetry acts on the corner of that square. You get a group which is transitive. You can make any corner in the square to be mapped to any other corner, but it's not too transitive because diagonals must be mapped into diagonals. So you cannot map a diagonal into a side of the square. So it's not too transitive. In general, whenever you get an element in the symmetric group, you get a subgroup in the symmetric groups, and that group contains an n cycle, you get something which is transitive. And you can just somehow reduce transitivity by considering stabilizers. So if you get a subgroup in Sn which is k-transitive, and then you fix the last element or any one in any number, and think of the permutations in P that leave that element fixed, then you get something which is k-1 transitive. So somehow the idea is that you can just probably go to the higher transitivity and then go down, although that is not quite correct. But well, and of course, if you have something which is k-transitive, this is transitive as well. But let me go for the higher transitivity. So if you believe in the classification of finite simple groups, then you got a completely classification of a k-transitive for k bigger or equal than 4 groups. So these are just the symmetric group, which is n-transitive, right? The alternating group, which is n-2 transitive, and then you got 4 little gems, which are the sporadic simple groups, thematic groups, which are m inside Sn for n equals 11, 12, 30, 23, 24. And these are 4 transitive and 5 transitive. So there is, I mean, the way it is constructed is just that the higher transitive, when you stabilize a point, you get the smaller transitive one. Okay, so and yeah, we are going to use at some point that these groups are kind of essentially unique in Sn. So I mean, of course, Sn is unique in Sn and An too, but you know, thematic groups are not unique in the sense that you can make a conjugation in Sn and get different copies. But somehow the representation of these groups are unique. Okay. So now let's try to fix or to solve problem 2 and fix an evolution algebra, and then consider the structure matrix, and consider this equation that was the only one that it was involved when considering automorphisms in an evolution algebra, right? And then start looking at that. Right? If the permutation group induced by that representation is transitive, so you can make any number into any number, right? And you make I and j to be the same, right? Then looking at these ones, so they are couples in which the two numbers are the same. Then that means that if one of them, because recall these scalars are not 0, right? So whenever you get one of these coefficients which is not trivial, then all of these coefficients are not trivial. But if one of them is trivial, then all of them are trivial. And if it is true transitive, in which you can make any two couples, not I and j being the same word, or I and j being the same one, then you can just play the same game and saying that either all of these are different 0 or all of them are 0, right? And in this last case, then the situation is kind of nice, because if you know it's an idempotent evolution algebra, since then whenever you square things, you don't get new vectors. Then that means that in that case is idempotent, so you need this coefficient to be non-zero because it's idempotent. And in that case, essentially your evolution algebra is just a direct sum of n copies of a one-dimensional evolution algebra. All these sets are essentially the same because it's two transitive. In particular, it's transitive, so you can just make each of these factors to be mapped into itself. And then in this case, the group of automorphisms of this algebra is just Sn. Right? So we are in this kind of situation. Either if it is transitive, all the diagonal elements in the structure matrix are 0 or not 0, and if it is too transitive, then all the elements outside of the diagonal have to be non-zero. So we are going to assume that we are now in having a two transitive representation, and the elements outside of the diagonal are not 0. So let's assume now that we got more than 3 elements in the base, so we can just apply this equality 3 times, and we get these new equations, right? And notice that this is a function depending of the 3 indices and the permutation. So the lambdas are not here. The lambdas are a consequence of this function. So the first result we got here is that if n is bigger than 3 and our representation is 2 transitive, then the lambdas are fully determined by the permutation. So essentially, the kernel of this representation is trivial, and then the group of automorphisms is just completely determined by the group of permutation induced, right? And then the second fun thing is that here in this set, we got just 1 index, and we got here 3 of them. So you can just make this a kind of a if and only if things, and that tells you that whenever you get this kind of function in which is independent of j and k, you get an automorphism, right? So in our situation, if we got 5 at least elements in your base and our group of permutation is 4 transitive, so essentially means that for any given permutation, I can just first change the second coordinate and leave the first and third coordinate, and so that we can just change this one, so it's independent of this one, or I can fix these 2 and move the third one using that is 4 transitive. I can make these functions to be independence of j and k, and I will get always this lambda and that will give me an automorphism. So in that case, again, the representation is fully determined by the permutations, right? The group of automorphisms is fully determined by the presentation, and this group have to be the symmetric group. So essentially what I'm saying is that there exist finite group permutations with abelian kernel, even factor ones, that cannot be realized as the induced representation, but an n-dimensional evolution algebra. To make this, okay, you will see this more clear in the next, because we are going to apply to a problem of the problem of classification of evolution algebras, right? So a classical problems in non-associative algebra is classify at least low-dimensional ones, and there's different approaches. So there is an approach via matrix theory or linear algebra, and there is an approach, recent approach by Ivan, Antonio Josué, Omar, that they use kind of a decomposition, but back in 2019, Sibonsa Isu, they proposed that instead of doing this kind of increasing the dimensions and trying to do some matrix theory, so essentially they were saying, okay, we are going to classify idempotent evolution algebras at dimension by dimension, but then the way we are going to classify is by looking to the automorphisms group. So the input will be the dimension and the automorphisms group. And they succeed that by classifying n-dimensional and idempotent evolution algebra such that the group of automorphisms is just the symmetric group, right? So we can just apply of a result and show that if we get the input will be a finite group, which happens to be a k-transitive group inside some symmetric group, then you will get an evolution k-algebra such that the group of automorphisms is G, right? And this is going to be an isomorphism. A priori, it's nothing related with this permutation representation. So you're going to get this evolution algebra X if and only if this group is the symmetric group. The way to prove this is just, well, we got this isomorphism, and this will give me a k-transitive group here, but not the actual representation. So then, if you remember the classification I gave you of a k-transitive group, then G is probably not simple, but it have not proper abelian normals a group. I mean, they could be the symmetric group, which is not simple, but the other cases are the alternating group, which are simple, and then the Matthew groups. So G have no proper abelian normals a group. And therefore, when I calculate this representation, the kernel is an abelian group, so there is no proper abelian group, so this must be faithful, right? So then that gives me another representation of a highly transitive group inside Sn. And I already told you that these groups are kind of unique, right? I mean, the representations is unique up to automorphisms of the target, right? So this gives us, again, another k-transitive group. And then we have seen that in this case, the group have to be the symmetric group. So yeah. So so that somehow classifies k-transitive groups and idempotent evolution algebras with given highly transitive group of automorphism. So now let me go to a variation of the problem too. So we are just the problem with the permutation representation that we gave you was that it was very fixed, and then the kernel, even the kernel was kind of fixed, but it's not the unique way that you can get a permutation representation out of an idempotent evolution algebra. So just consider X to be any idempotent evolution algebra with a natural basis, and then make a kind of a decomposition of this base, and then consider as subset of that in which all the elements are idempotent elements, right? So I will call them these natural idempotent elements in my permutation, in my natural base. Then for any given automorphism side, what I get is that when I map an element in this set of natural idempotents, I map that thing, I got another element in the base, but when I square, I get this square, and then that means that essentially the scalar have to be trivial, and then this element have to be an idempotent. So essentially we can think that this permutation is indeed an element of the symmetric group of M letters. So we have a new presentation, a new permutation representation in which the group of automorphisms of our idempotent evolution algebra maps to a symmetric group, which is strictly smaller. Well, I mean, not really, but could be strictly smaller than our original one, because we are considering only idempotent element. And just notice that we have no control on the kernel of this math, because indeed, if your evolution algebra have no idempotent natural element at all, right, then this representation will be the trivial representation. So this will be the trivial map, right? So in this situation, we have a wider catalog of a wider range of situations in which we can think of this problem 3, in which we are going to ask the same like problem 2. We have an idempotent evolution algebra with a set of idempotent elements, and we have an induced representation, and we ask which permutation representations can be realized of the induced representation by a finite dimensional idempotent algebra on the idempotence natural elements. And our main theorem is just that, well, given any any permutation representation, could be even not faithful, could be even the trivial one. You can always find an idempotent finite dimensional evolution algebra over any field you will like, such that the group of automorphisms is the group you start with, and then when you consider this representation, you recover the original G. So how we prove this? So, well, we recall that I was explaining the first solving problem one with a finite graph. So we do something similar, right? So first we got a theorem by Costoya, David Mendes, and myself back in 2019, in which we proved that given any permutation representation of a finite group, you could always find a nice graph. And by nice means that the graph have the group of automorphisms isomorphic to G, where G is this the group you start with. And then if this graph, the set of vertices is split into different subsets, each of them is out of G or G invariant. So wherever every automorphism of the graph maps V null into V null and V1 into V1. And the funny thing is that this first subset have the same side M that the permutation representation you got one. So then when you see how the group of automorphisms, which is G, acts, permutes these vertices, so the group of permutations of these vertices, the group of symmetries of these vertices is isomorphic to Sn, then you recover the original, well, this should be G, right? You recover the original permutation you start with, right? So then what you do is just choose any element, any unit in the ground field, and we now construct an idempotent evolution algebra as follows. So we make a kind of a modification of the constructions we did for solving problem one. So as a vector space, or evolution algebra is spanned by the vertices and edges of this graph. And now the multiplication for the vertices is just U squares U for just the vertices in this V0, which were the ones inducing the representation. So this will become independent, the idempotence. For the other vertices, what I do is just U square to get themselves, but then you somehow twist them or perturb them by making you add all the vertices, and then you multiply by a scalar, right? So this is again G invariant because vertices are mapped to vertices, and you get this is a non-trivial scalar, and then you are having more than one vertices. So this is non-zero. And finally, at the level of edges, you keep on having the same multiplication table you used to have it. So each edge square gives you the edge itself, and then the vertices that edge connect, right? So now, again, the group of automorphisms of this evolution algebra maps these are idempotent, so they are mapped to themselves. Then somehow the edge, the vertices are indeed ideal of the algebra, so they are mapped to themselves. So and the edges to edges. So this I mean, for this algebra, the group of automorphisms of the algebra and the group of the automorphisms of the graph are the same. But then these are just the idempotent. When you restrict, you get the actual representation you start with. And thank you. I think I was pretty fast. I apologize because I never know how to control time in these online things. But well, if you want to read more, I mean, the details of these things are written down now and will be by the end of the year, will show up in archive. And then the other reference I have used are just these first 2 pages in which we proved that the evolutions algebras can realize any finite groups or any perfect group in this case. In this paper by Alberto Luque and Alicia Ladra is where the automorphism group of an idempotent evolution algebra is described as a exact sequence, and this paper is where this idea of using automorphisms to classify evolution algebra is presented. That's all. Thank you.
Thank you, Antonio. Are there any questions or comments?
Well, I have a question, may I ask?
Yep.
Okay, so my question is the following one. Is something known about classification of simple evolutionary algebras?
Oh, well, only in low dimensions. I don't know about higher dimensions. No. I mean, okay, there is a way to think of that, right? Because if this simple, then it will be idempotent. And if it is idempotent, you can describe that in terms of a graph, right? So you can just think of there is just one natural base. So you think of elements in that natural base as vertices in your graph, in your quiver somehow, and then you narrow from one element in the base to another element in the base, wherever the square of that element involves a linear combination of the second one. So classifying simple evolution algebra is like classifying simple quivers with weights on the arrows, right? And then the difficult thing is that you have to check whether two different quivers with different weights in the arrows give the same simple evolution algebra. So it's a problem in linear algebra and a non-standard action of the normalizer of the maximal torus on the matrices. Yeah. But I mean, oh, there is.
Okay, so thank you.
You're welcome.
Okay, there's also a question on the chat.
Oh, if there are derivative algebras related to operands.
I think you've frozen again, Antonio. Don't know if you can
I
hear
don't know.
me.
I must confess, I asked before. Florin was asking whether there are derivative algebra associated operands. Oh, it says my connection is unstable. Can you hear me?
I can hear you now. Yes,
Yeah.
thank you.
Okay. So Florin was asking whether there are operands associated to. I mean, there are derivation, of course. But I don't know whether there are operands associated to evolution algebras. I mean, whether evolution algebras are operatically defined. Although I was asked that by a colleague here that works on operands, Jose Manuel Moreno, but I don't know the answer to that one.
Okay. Are there any other questions or comments? Okay, then can we thank Professor Viruel in the usual way then? Thank you.
Thank you.
Okay, well, the next talk will start in a little over 10 minutes time, again on the hour, 1300 GMT. So short comfort break before the next talk commences.